It is negative 34 degrees outside. The wind is moving through the trees like something alive. Every breath of cold air that finds a gap in your wall doesn't just chill the room, it steals from your wood pile, steals from your fuel budget, and in the worst conditions, it steals from your safety. Most men building Quonset huts in cold climates make the same mistakes not because they are careless, not because they don't work hard, but because nobody told them where the heat actually goes. Nobody showed them the invisible pathways, the thermal bridges, the moisture traps, the pressure gaps that turn a promising off-grid shelter into an ice box that swallows firewood and spits out frost. This video is going to change that. What you are about to learn comes from the men who figured it out the hard way, Alaskan builders, remote homesteaders, and cold climate engineers who tested these solutions across decades of brutal winters. 7 specific habits, each one targeting a different failure point in the Quonset hut design. And when you apply all 7 together, you stop losing 90% of the heat you are paying in money and sweat to generate. Your Quonset hut right now is essentially a giant radiator pointed at the Alaska wilderness, a curved metal shell pressed against frozen ground, full of metal ribs that conduct cold air like copper wire conduct electricity, with end walls that most builders drastically underinsulate because they are focused on the dramatic arch and forget the flat surfaces on either side. The cold doesn't wait. It finds every bridge, every gap, every reverse vapor layer, and it gets in. But here is what the smart men discovered. You don't need to rebuild. You don't need a bigger stove or more firewood. You need 7 habits. Start applying them, even partially, and you will feel the difference before the season is over. Let's get into it. The first habit addresses the single largest heat loss point in the entire Quonset system, and most builders never even think about it until the hut is already sitting on its foundation, and it is too late to fix without tearing things apart. Where the curved metal shell meets the concrete slab or the ground, there is a joint. That joint is where 2 of the most thermally different materials in your build come into direct contact. Steel is an exceptional conductor of heat. Concrete is not far behind. When those 2 materials touch without any barrier between them, you have created a thermal express lane. Heat from inside your hut travels down the walls, hits the metal to concrete connection, and bleeds straight out into the ground. The ground in Alaska during winter sits at temperatures that would shock most people. That thermal gradient, the difference between your warm interior and the frozen ground below, is enormous, and the greater the gradient, the faster the heat moves. The fix is called a thermal break. It is a layer of material. Rigid foam board works extremely well. Rubber gasket material also works, installed between the base of the metal shell and the top of the foundation before the structure goes up. This layer has almost no thermal conductivity. It physically interrupts the pathway. Heat trying to travel from your warm steel walls down into the cold concrete now hits a barrier it cannot efficiently cross. Here is the brutal reality of ignoring this. A single unbroken metal-to-concrete contact point around the perimeter of a standard Quonset hut can account for up to 25% of total heat loss in extreme cold. 1/4 of everything your stove produces, disappearing into the ground. The thermal break costs almost nothing compared to the structure itself. A roll of foam gasket material, a few sheets of rigid board, but it requires being installed before the hut goes up, not after. This is a habit that has to happen at the very beginning, which is exactly why so many men skip it. They are excited to raise the arch, and they underestimate what happens at the base. If your hut is already built and you did not install a thermal break, you are not completely out of options. Exterior rigid foam insulation packed tightly against the base and sealed with weatherproof caulk can partially mitigate the damage. It is not as effective as a proper pre-built thermal break, but it reduces the bleeding. Do it this autumn before the ground freezes. The second habit is about the ribs. Look at the inside of any Quonset hut, and you see those curved steel ribs running from floor to apex. They are the skeleton of the structure. They are also, from a thermal standpoint, one of the most destructive features of the design, because every single one of those ribs is a direct metal pathway from your cold exterior shell to your warm interior space. This is what builders call a thermal bridge. The metal rib touches the outer shell, which is cold, and it also touches or comes extremely close to your interior wall surfaces, which are warm. Metal conducts that temperature difference efficiently and continuously. Even if you insulate the cavities between the ribs perfectly, if the ribs themselves are left exposed and bridging, you lose a significant amount of that insulation's value. It is like building a perfectly insulated wall and then running steel rebar through it every 16 inches, leaving ends exposed on both sides. The habit is to spray foam the rib cavities before you add any interior wall panels. Not after, before. You fill the spaces between the ribs completely, and critically, you also coat the surface of the ribs themselves, encapsulating them in foam, so they are no longer directly connected thermally to the interior air of your hut. Closed-cell spray foam is the material of choice here. It has a high R value per inch, typically between 6 and 7, and it forms an air-impermeable seal. That air seal matters as much as the R value, because in a Quonset hut, even tiny gaps in the insulation layer allow cold air infiltration that standard batt insulation cannot stop. The foam gets into every irregular curve, every gap around the rib flange, every place where batt insulation would bow, compress, or leave a void. Men who have done this report a dramatic change, not just in temperature, but in how the hut feels. That persistent cold radiating from the walls disappears. The interior surfaces stop feeling cold to the touch. The stove cycles less. This single habit, applied correctly, cuts thermal bridging losses to a shell by 60 to 70%. The third habit is the one most people get wrong in the worst possible way, and the consequences don't show up until midwinter, when suddenly you have water running down the inside of your walls, frost forming on the metal, and insulation that has absorbed moisture and lost half its effectiveness. Moisture control in a Quonset hut is not the same problem as moisture control in a conventional framed house. The curved metal shell is vapor impermeable. Warm interior air that contains moisture, from cooking, from breathing, from a wood stove, migrates toward the cold shell. When it hits the metal, which is at or below the dew point, it condenses. That condensation is the beginning of your problems. The solution is a double vapor barrier system installed in the correct sequence. And the sequence is everything. Against a metal shell, you install rigid insulation. Polyisocyanated board is ideal because of its high R value and its resistance to moisture absorption. This layer keeps the metal shell warmer, raising the dew point surface temperature, so condensation is less likely to form. Then you install a vapor barrier, 6 mil polyethylene sheeting, sealed at every seam and edge with vapor barrier tape. Then a second layer of insulation, typically mineral wool, or another layer of rigid board. Then a second vapor barrier, or a smart vapor retarder that adjusts its permeability with humidity levels. The logic behind a double layer is this. If any moisture gets past the first barrier, it needs somewhere to stop before it reaches the cold metal. The second barrier catches it. The rigid insulation between the barriers keeps the inner surfaces warm enough that any captured moisture cannot condense further. It is a redundant system, and in Alaska, redundancy is not paranoia. It is engineering. Getting this wrong. For example, installing a vapor barrier tight against the interior wall surface and leaving the outer layer of insulation unprotected traps moisture between the barrier and the cold shell. You have just created a perfect environment for corrosion, mold, and insulation failure. Men have torn out entire interior wall systems in February because of this mistake. The cost in time, materials, and misery is significant. The correct installation costs the same as the incorrect one. It just requires knowing the sequence before you start. Now here is where a lot of instructional content loses the viewer. It runs through the habits mechanically without connecting them to the physical reality of what is happening inside the hut. So let's be specific about what your situation looks like right now if you are ignoring habit 4. Your end walls are flat. They are large. And in most Quonset hut builds, they are dramatically underinsulated compared to the curved shell. Partly because the shell is visually dominant and gets all the attention, and partly because flat framing feels straightforward, and builders underestimate how much insulation a flat wall needs in extreme cold. In interior Alaska, where temperatures regularly drop below -40, the recommended minimum for an end wall in a heated shelter is R40. Many standard builds come in at R19 or R21, less than half of what the climate demands. That gap represents a staggering amount of heat loss through two relatively small surfaces. The habit of aggressively insulating end walls starts at the framing stage. Use 2x6 framing instead of 2x4 to get more insulation depth. Add a continuous layer of rigid foam to the exterior face of the framing before the outer cladding goes on. This eliminates thermal bridging through the studs and adds substantial R value without touching the interior space. On the interior, fill the stud cavities completely with closed-cell spray foam rather than bad insulation. Batts compress sag and leave gaps that defeat the purpose. The additional cost of hitting R 40 on both end walls compared to hitting R 19 is not dramatic, but the thermal performance difference over a winter season is enormous. End walls that are properly insulated stop feeling like cold panels and start feeling like neutral interior surfaces. Your stove's heat stays in the room rather than bleeding out through the largest flat surfaces in the structure. Habit 5 is one that many men initially dismiss as unnecessary, and then they build it and wonder why they waited. Every time the door of your Quonset hut opens, you lose a volume of warm air equal to the size of your entry opening, and you emit the same volume of cold outside air. In a conventional house in a cold climate, this is managed primarily by the fact that the entry is often protected, a porch, an overhang, some architectural buffer. In a Quonset hut in Alaska, the door frequently opens directly to the exterior environment. The pressure differential between your warm interior and the cold outside amplifies the problem, pulling cold air in at the floor while heated air escapes at the top of the door frame. A vestibule, sometimes called an airlock entry, is a small enclosed space built at the door. It can be as simple as 4 feet by 4 feet. It does not need to be elaborately finished. It needs to have 2 doors, one between the vestibule and the exterior, and one between the vestibule and the hut interior. The principle is that both doors are never open at the same time. When you enter, you step into the vestibule, close the outer door, then open the inner door. The vestibule holds a small volume of air, much smaller than your hut interior, and any cold air admitted in the process of entering affects only that small volume. The math on this is striking. A family-sized Quonset hut might have interior air at 65 degrees Fahrenheit. Every unmitigated door opening in severe cold can drop the interior temperature by several degrees, forcing the stove to recover. Over a day of normal activity, 8 to 12 door openings, the cumulative heat loss and stove recovery cycles are significant. A vestibule eliminates approximately 80% of that loss. Build it with the same insulation standards as the hut itself. An uninsulated vestibule is better than nothing, but an insulated one with a weather-stripped outer door performs dramatically better. Men who add vestibules to existing Quonset hut builds consistently report the change as one of the most immediately noticeable improvements they made. Habit 6 is about physics inside the hut, specifically the fact that heat rises, and the geometry of Quonset arch ensures that a significant portion of your heated air ends up far above the space where you actually live. The apex of a Quonset hut can be 10, 12, or 14 feet above the floor. Warm air being less dense than cold air rises continuously toward that peak. In a rectangular room, this effect is moderate. In an arched structure with a concentrated high point, it is amplified. The temperature differential between the apex and the floor of a Quonset hut in winter, with no active circulation, can be 8 to 12 degrees Fahrenheit. You are sleeping and working in the cold zone, while a significant portion of your heated air pools uselessly above your head. The wood stove placement matters more than most builders realize. The optimal position is toward one close in the hut, not in the center, not near the door. Placing it toward one end creates a longer thermal travel path through the interior, which distributes heat more evenly through the living space. Elevating the stove slightly, on a proper heat-rated platform 8 to 12 inches off the floor, improves radiant heat distribution at the level where it matters most. The second component of this habit is active circulation. A small low-wattage fan, positioned near the apex of the arch, runs continuously on low speed and pushes the accumulated warm air back down along the walls. The cost to operate a small fan continuously is negligible. The temperature recovery at floor level is significant, typically 4 to 6 degrees in a well-sealed hut. That means your stove runs less, your firewood lasts longer, and the comfort level in the space improves substantially because you are no longer heating the top of the arch as your primary output. Some men add a second small fan near the stove itself, positioned to move the immediate radiant heat laterally into the space rather than allowing it to rise directly to the apex. These two fans together, one at the stove, one at the peak, create a circulation pattern that makes the entire interior volume of the hut usable heated space rather than a stratified system where the top 12 inches contains most of the heat. The 7 habit is the one that separates men who build a hut and maintain a hut from men who build a hut and slowly lose it. Metal and insulation behave differently under temperature changes. Steel expands and contracts with every thermal cycle, and in Alaska, those cycles are extreme. A Quonset hut shell goes from deeply cold in the night to warmer in the afternoon sun, then back to cold again. Over hundreds of cycles through a single winter, and thousands across several winters, the metal shell moves. Not dramatically, not visibly, but measurably. Spray foam insulation is rigid. It does not flex with the metal. Over time, the bond between the spray foam and the steel shell, even a chemically adhesive bond, can develop microgaps. These are invisible from inside the hut. They might be a fraction of an inch wide, but in extreme cold, a fraction of an inch is enough. Cold air infiltrates the gap, travels along the shell surface inside the insulation layer, and shows up as cold spots on your interior wall. Your thermometer might not change, but your comfort does, and your fuel consumption rises without an obvious explanation. The annual inspection habit is simple. Every autumn, before temperatures drop, you go through the interior of the hut systematically. You use a thermal camera. They are affordable and widely available now. Or simply run your hand slowly along every wall surface on a cold day, feeling for temperature variations. Anywhere the wall feels noticeably colder than surrounding areas, you have found a gap. You mark it. Then you inject spray foam into the gap from the interior side, using a foam gun with a thin extension nozzle that can reach into narrow spaces. You seal it. You move to the next one. This inspection takes a few hours. It costs the price of a can or two of spray foam, and it catches a progressive failure of your insulation system before it compounds into a serious problem. Men who do this every year report that their huts perform better in year 5 than they did in year 1, because each inspection catches small failures before they become large ones, and the cumulative quality of the insulation layer actually improves over time rather than degrading. The thermal camera also reveals something important. It shows you not just where gaps have formed, but where your original insulation was imperfect. First-time builders almost always leave some areas underfoamed or with thin coverage. The autumn inspection in year 1 is often the most seductive because it catches original installation deficiencies, while they are still easy to address. Now, let's bring it together with numbers, because this is where the abstract becomes real. A Quonset hut with none of these habits applied, in interior Alaska, through a standard winter, can consume 4 to 6 cords of firewood if wood heated. That is a significant amount of labor to cut, split, and stack, or a significant fuel cost if you are purchasing it. The same hut with all 7 habits applied. Thermal break at the foundation, spray foamed ribs, double vapor barrier system, aggressively insulated end walls, vestibule entry, optimized stove placement with circulation and annual inspection, typically consumes 1.5 to 2 cords of firewood through the same winter. The reduction is between 60 and 75%, depending on the hut size and the specific winter. That is not a marginal improvement. That is a fundamentally different relationship between your shelter and the cold. A hut with these habits applied can hold 65 degrees Fahrenheit at an exterior temperature of -30. Without them, the same stove working at the same output struggles to push the interior above 50 in severe cold. The habits also protect the structure itself. Moisture infiltration destroys insulation, corrodes metal, and rots any wood framing over years. A properly vapor-controlled, well-inspected Quonset hut will outlast one with uncontrolled condensation by decades. None of these 7 habits require exotic materials or advanced construction skills. They require knowledge in sequence, doing the right things in the right order at the right stage of the build. Most of the critical work happens before the hut feels like a hut, before the interior is closed in and livable, which is exactly why so many builders skip it. When you are in the middle of a build, and the structure is going up fast and looking impressive, stopping the foam ribs and install vapor barriers feels slow. It feels like delay. It is not delay. It is the difference between a hut that works and a hut that fails quietly over time until you cannot afford to heat it anymore. Build it right the first time. Inspect it every autumn. Treat the thermal envelope as seriously as you treat the structural shell. Because in Alaska, the thermal envelope is not a comfort feature. It is a survival system. Apply these 7 habits. Know where your heat goes. Stop giving 90% of it away to the wilderness, your wood pile, your fuel budget, and every cold night you spend actually warm inside the hut will tell you exactly how right this approach was.